Now that we've learned about dichotomous data, let's turn our attention to Bernoulli events. A Bernoulli event is a random event that results in one of two possible outcomes. In other words, it yields dichotomous data. A key that is important here is that it is a random event. What about that name Bernoulli? Bernoulli events are named after Jacob Bernoulli, who was a Swiss mathematician. Let's look at some sample Bernoulli events. If you flip a coin, it is random, and you will get one of two possible outcomes. So that means it is a Bernoulli event. It has met both of the conditions for a Bernoulli event, random and yields dichotomous data, two outcomes. Now, rolling a die is random, but that can yield six outcomes. But remember, any data can be made dichotomous. So we could, for example, say, is it a 6 or is it not a 6? Now, what about research? How are Bernoulli events generated in research? The key is random selection. So randomly select a participant from an accessible population. Will this participant vote yes on the school bond issue? Again, it's a Bernoulli event because we randomly selected this individual from probably a roster of voters, and we obtained dichotomous data, that is a yes or a no. What about someone who was given a treatment? They're cured or they're not cured. Again, if we've randomly selected a participant and then observed whether or not they're cured, it's a Bernoulli event. Did this person earn at least 80% on the exam? Randomly select and look to see if they earned at least 80%. Randomly select and see if the person can successfully complete a task, yes or no. Randomly select and see if this person achieved mastery, yes or no. Now, when using a match pair design, there are actually two potential random aspects: random selection of participants, and after matching, random assignment to the treatment or control condition. This can then yield a Bernoulli event. Did the treatment member of the pair perform at a higher level than the control member of the pair? This would be a random event even if the participants were not randomly selected, but rather we randomly assigned each member of the match pair to a treatment or control condition. Then the fact that the treatment member of the pair performed at a higher level than the control member of the pair would be one of two possible outcomes, the other one being that the control member of the pair scored higher than the treatment member. For a few minutes, let's look more generally at events, including but not restricted to Bernoulli events. Joint events are multiple events in the same study. Here's an example with 7 events. We have event 1, 2, 3, 4, and so forth, all the way to event 7. In fact, let's go ahead and simplify the notation. We'll use E for an event, a subscript K to indicate which event, and then we will change K from 1 to 2 all the way up to capital K, which in this case would be 7, the number of events. Let N sub K be the number of possible outcomes for E sub K. So if event 1 has, say, 4 possible outcomes, then N sub 1 would be 4. If event 2 has 7 possible outcomes, then N sub 2 would be 7. If event 3 was, say, a Bernoulli event, so it had 2 possible outcomes, then N sub 3 would be 2. Notice that N simply stands for how many possible outcomes there is for a particular event, and notice in general that any of these events could have any number of outcomes, and it doesn't even have to be the same for each event. Now suppose that we would like to calculate the total possible number of outcomes. The total number of possible joint outcomes is simply the product of those n's. So how many possible outcomes there are for the first event, how many possible for the second, how many possible for the third, they're all multiplied together all the way up to however many possible outcomes there are for the last event. Let's look at an example, and this time, let's go ahead and stick with Bernoulli events since that's what we're learning about. Flip a coin 3 times. Each of these 3 events has 2 possible outcomes. The number of possible joint outcomes is 2 times 2 times 2, or 8, because n1 is 2, n2 is 2, n3 is 2. Multiply those all together, we have 8 possible outcomes. Here are all the possible outcomes. We could get heads on the first flip, heads on the second, heads on the third. We could get heads on the first flip, heads on the second flip, tails on the third, and so forth. This yields 8 possibilities for what we get on all 3 flips of the coin, all 3 Bernoulli events. Let's look at another example, but this time let's give it a little bit of research context instead of a coin flip. Administer a treatment to 3 patients. Each of these 3 events has 2 possible outcomes. The number of possible joint outcomes is 2 times 2 times 2. That is, we have 2 possible outcomes for each event because they are Bernoulli events yielding dichotomous data. We multiply those 3 2's together and we get 8. This looks just like when we flipped a coin, but here, instead of heads and tails, we have Y's and N's to represent yeses and nos. A Y means the individual improved, or perhaps it could mean that they were cured with the treatment. If we're using a match pair design, the Y could mean that the person in the treatment condition improved more than the match in the control condition. Notice that there are 8 possibilities ranging from everyone being cured to no one being cured. We know that there are multiple potential outcomes with joint events. In the example we've been looking at, there are 8 of them. In a study, however, we only observe 1 outcome. What we observe in a study can be visually portrayed in a graph and described with statistics, like this. In this case, what we're showing is that we had 67% cured, 33% not cured. Here's a graph. Here are statistics. Graphs and statistics always go hand in hand, where the statistics are used to drill down into what the graph displays, the graph displaying the major features of the data. It gives us a quick overview, but when we need to get more specific, we turn to the statistics. Any cure rate between 0 and 1, that is 0% or 100%, non-inclusive, in other words, not including 0 and 100%, but only anything between those, could result in any of the possible joint events, including the one that we observed. So we could have had a cure rate of, say, 20%, or a cure rate of 82%, or a cure rate of 7%, and we could observe any one of these possible 8 outcomes. The goal is to determine the cure rate that we cannot observe based on the data that we can observe. What we really want to know is the cure rate, yet we have only made 3 observations. Never forget, what we observe when we use a maximum likelihood statistic, or an MLE, is the best single guess we can make for the cure rate, and proportions are maximum likelihood estimates. Consider a population of interest. Imagine that we applied a treatment to everyone. This could be a medical treatment. It could be an educational intervention. We're using the term treatment broadly here, so it could be any type of intervention. Now, we cannot measure everyone, so we draw a sample. And once we draw a sample, we observe and we determine the outcomes of the Bernoulli events. We can describe these outcomes with a statistic. Thus, it is a descriptive statistic. It describes what we observed with our sample. Now, the idea that we applied the treatment to everyone in the population is unrealistic, just as we cannot measure everyone. So instead, we sample first and then only apply the treatment to the members of the sample. Now, note the logic here. The Bernoulli events we observe after applying the treatment to the members of the sample are the same as what we would observe if we applied the treatment to the population and then selected a sample. So we would obtain the same outcomes either way if we applied the treatment to everyone in the population and took a sample, or if we sampled those same individuals and then applied the treatment to them, we would still get the same Bernoulli outcomes. Thus, we can make an inference about the characteristics of a treated population based on the observations in the treated sample. This means that our descriptive statistic, once used as a description of the sample, becomes an estimate of the population parameter. It plays both roles. Note the hat to indicate it is an estimate of what is under the hat. Let's summarize the key points and look ahead to how we might apply these ideas in our research studies. A Bernoulli event is an event with two possible outcomes. For a sample of a specified size and a Bernoulli response variable, we can determine in advance the number of possible joint outcomes. We can obtain a sample and look at the relative occurrence of Bernoulli event outcomes, then estimate the relative occurrence in the population.